So the things we will discuss, we will describe the method, then we will talk about the general procedure of applying the method, then we will talk about tips for practical application of the methods. As you know, some of these methods in theory won't apply exactly in practice, so we will talk about the tips you need to know. Then we will go through a manually solved example, which will make you understand what the machine will be doing when it's solving a classification problem with K and N. And then we will talk about the strengths and limitations and when this method is good to use and when you should think about other classification methods to use. In the next video, we will talk about implementing K and N in R. Now, let's describe the method. So first of all, we need to understand that the method is a classification method. So our aim is to classify a new observation to a class that we know. So basically, if we have a data set with 3 or 4 labeled classes, we are trying to assign a new observation for which we don't know the class to one of these classes. So as the graph here describes, we have 3 classes, for example, and we have this white circle or white point, and we would like to know, should it fall under the green class, or should it fall under the red class, or should it fall under the blue class? So the features of K and N classification problem is that it's a supervised learning technique, meaning that like most of the classification methods, it starts with labeled data. So we have a training data that we know the classes of. So for example, we have these points where we know they are green, we have these points where we know they are red, and similarly with the blue points. It's non-parametric, so really we are not assuming anything about the distribution of the data, unlike some of the methods such as, for example, LDA, which is assuming linear or normal distribution of every class of the data set. For this method, we're not assuming anything, we're just getting the data with no assumptions. So it's a non-parametric method. And the outcome, of course, like all classification problems, is categorical. So in the end, we're gonna say it's green, it's red, it's blue. We're not gonna say it's 60.5% this color and 40% this color and so on. It's a category, and that's our end of the classification. So how does K and N classify? Very simply, it looks for the K nearest points and checks their classes, and then count the number of classes represented in the K nearest points and assign the new observation to the class with the majority. So for example, if we are using K equal 1, which means we are looking only at the closest neighbor, so here it's a little bit difficult, but I can see that it's a lot closer to the green, or a little closer to the green than the other two. So if we're using K equal 1, it will be green. If we're using K equal 2, it will be probably a tie between those 3. So it could be, when we have ties, we go with either class. So it could be any of these classes. But if we are using K equal 4, it will surely be blue, because we're looking at these points, and the majority of the points from the 4 are blue, 2 out of 4. Whereas the red and green are 1 and 1, so it will be a blue point, and so on. So the procedure of applying this method is first to choose K. As you've seen from the previous slide, we talked about K equal 1, we talked about K equal 2, up to K equal 4, and we've seen different classifications. So really the first thing we need to agree on is what K value to use. And this is done by applying different values of K, and then checking with the validation set how much of a correct classification rate we are getting, and going with the best K that gives us the best correct classification rate. And we will see this in a practical example. The second thing we need to worry about is agreeing on a distance metric, because we talked a lot about nearest, 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 and from nearest we understand that there is somehow a concept of a distance. So we need to use a distance to measure how close these points are. Most commonly, Euclidean distance is used, which is the normal distance between 2 points. But Euclidean distance sometimes is limited because some variables might be more important than others, so we might want to use weighted distance. So anyhow, we need to agree on a distance metric to use. Then we will find the K nearest points for each unlabeled observation. So for example, here we have 4 unlabeled observations. We will start by trying to find what are the k nearest points. If we agreed on k equal 2, we will find the two closest points to each point from here, from the training data set. If we talked about k equal 3, we will find the 3 nearest point to every point in our new observation from our training data. So we will look at the closest labeled points to every point. Finally, we will count the observations out of the k neighbors falling in each class. So we will, for example, we will see that the closest points to these, if we are talking about 5 nearest neighbors, it will be 4 green and 1 red for this point. It will be 3 blue and 2 and 1 green and 1 red for this point, and so on. So we will count how many points are represented by each class from the k nearest neighbors. And finally, we will label the new observation with the class of the majority of neighbors. So if the majority are of a certain class, then we have our classification method or strategy telling us that this observation is most probably of that class 2. And this is, in a nutshell, is the procedure of applying k and n. Now for the practical application. The first thing we need to know is that we need to standardize the covariate data. Just imagine with me for a second if x1 is measured on units of thousands, while x2 is measured on units of ones or tens. We will definitely be biased toward the points closer on the x1 axis than the points closer on the x2 axis. Because if you look at the Euclidean distance formula, it will just subtract the difference between those two covariates and then square it and take the square root. So when we talk about different scales, we will be biased towards the axis with the largest scale. So we will kind of ignore the other one. So therefore, we need to standardize the data, make sure that the data is all standardized, preferably around centered around 0, and have a standard deviation of 1. And this is common in many statistical applications. Then we need to choose the appropriate distance metric, as we mentioned, if we have different importance for different variables. Like for example, if we know that x1 is more important than x2, we might care about the points that are closer on the x1 axis more than the points that are closer on the x2 axis. So depending on whatever understanding of the problem we have, we might want to use weighted distance to give more covariates, more power over the others. If the covariates are binary also, so for example, if we are having covariate patterns of zeros and ones, we might want to use a similarity matrix of distance. So for example, we can look at the Jacquard index, which will look at how many values are similar in every covariate. So for example, it will count the number of ones that are similar in the same location for both number of zeros, and then divide by the total number. So you can look up distance metrics to find the most appropriate metric to use. And there are a lot of Wikipedia articles that are very well written and navigated around the different distance metrics that you can use. Also, we need to think about what values of k would provide an additional benefit. So we talked a lot about ties. So for example, if we have binary classification where we only have 2 classes, it's wise to use a k that is odd, because eventually none of the classes will be equal to the other. We will always have one that is more than the other. So we will avoid the ties, which gives us also like a benefit of not having to randomly assign once we have a tie. But this will not work if we have more than 2 classes, so it's something also to think about. So basically, to choose the optimal k, we need to check the correct classification rate against the different k values for the validation data. So we will try out different k values, and the one that gives us the best correct classification rate for the validation data will be the one that we use for our further classification. Now let's go into an example, which is the more of the part that you will understand most of what's going on with this technique. So like any classification problem, we will start with labeled training data. So in this case, for example, we have data on 2 dimensions, x1 and x2, and we have the classes, and we have, I think, 7 observations in our training set. And they will look like this. It's useful to envision them with the colors. So now we know how every class is distributed. So we have 2 green points, 2 red points, and 3 blue points. And they are on a scale of 2 dimensions. One is going from 0 to 4.5 and one is going from 0 to 4. So it's kind of on the same scale. We don't need to worry about scaling. Now we will also have validation data that will help us tune the hyperparameters of the model that we are using. So we're using K and N, so we will use the validation data to select the best K. And validation data is data that we know the labels of, but we're acting like we don't know. And then we are checking what was our classification correct or was it not, and selecting the hyperparameter based on this. So this is represented by these black points that have a colored outline. Finally, we have the test data, which is the new observations, which are the ones we are trying to classify. So the test data in a practical problem will be ones that are also labeled because they're coming from our original data set, but we act like we completely don't know their labels. And we use them to finally check how our method is performing, and it kind of gives us an indication on the out of sample error, as we call it, which is how our method will perform in the population that we don't know. So we will act in this problem, we will act like we don't know the classes of the test observations, and our aim is to classify them. So we have 2 white points over here for which we are aiming to classify, whether they are red, blue, or green. What are the questions that are common? First, what is the best K to use? We will test from K equal 1 to K equal 3 and determine what K value should we use. And then we want to classify these white points. So now this is our graph of the problem, having the training data and the validation data. And the solution steps is to first, for every new point, calculate the distance to all label points to find the nearest neighbors. So for a human being, it's easy to find the closest points from a 2D graph. But imagine for a computer, it will have to calculate the distance from all the points and then sort them and decide what are the closest points. And also for a human being, if it's not 2D, if it's 10 dimensions, there's no way that you will be able to graph them in order to select the closest points. So you will always have to calculate the points. So to do this, first your points should be indexed. So for example, we need to know the kind of index of each point so we can calculate the distance between it and every validation point. So I labeled the validation data points by A, B, C, while labeled the training points with 1, 2, 3, 4, 5, 6, 7. So the first thing we need to know is to find the nearest neighbors of every validation point. So for A, we need to calculate the distance between A and every point in our training data set and calculate the distance for it. And we need to do the same for B, and we need to do the same for C. And this is the aim of finding who are the K nearest neighbors to A, to B, to C. To do so, in this example, we will use the Euclidean distance. As you're familiar with the Euclidean distance, or you can look up the formula, it's very easily done. So basically on x1, we will find what is the value of A and what is the value of point 1. On x2, we will find what is the value of A and what is the value of point 1. And we will subtract the difference and square it and sum all the differences. So we will find that A to 1, the distance is 0.5. So we will just log 0.5. So now we know that the distance between A and point 1 is 0.5. Now we want to calculate the distance with A2. Again, we will find the, so x1 value of A is 1, x2 value of A is 1.5, while x1 value of 0.2 is 1.5, and the x2 value of 0.2 is 1.5. So we will just find the distance, again, subtract them, and apparently it's 0.5 as well. And we will do this for every point in our data set. So basically, we will do it for all the same way, and we will find these distances. Now, we kind of have the distances, but what we need to know is what are the closest points, because we're talking about the K nearest neighbors. So to do this, we will just sort the distances from closest to furthest. So for example, for A, we can say that the closest points are 1 and 2. And actually, you can see this from the graph too. And then comes the point number 6, which is this one. And then comes probably point number 7, which is this one, and so on. So what we will do is sort the points. As you can see, they were sorted over here now. So the closest neighbors to A go from 1, 2, 6, 7, 5, 4, 3. And for B, the closest one is 7, then 5, then 6, and so on. For C, the closest one is 5, then 7, then 6, then 4, then 3. So now that we have sorted distances, we can start checking what k value can we use. So we will assume, for example, that we are using k equal 1. We will check what is our correct classification rate, and then check for k equal 2. We will check what is our correct classification rate and do the same for 3. And we will choose the k that gives us the highest correct classification rate. So for k equal 1, of course, we will only worry about the first point, the closest point to that new observation from our validation data set. And in this case, for A, it's 0.1. So this is the closest neighbor. For B, it's 0.7. This is the closest neighbor. And for C, this is the closest neighbor. So now what we need to do is to check the class of each of these points. So for example, for A, the closest neighbor is 1 with a distance of 0.5, and its class is green. So our prediction, because we're using k equal 1, so it's 1 nearest neighbor, is that A is green. Now we ask ourselves, is it correct or is it wrong? So we know because it's a validation data set, we know that it's supposed to be green. So we can say, yes, our prediction was correct. Now for point B, the closest point is 7 with a distance of 0.35. And its class is red. So our prediction for point B is red. Now, is this correct? Again, it is correct. For C, the closest point is 5, and with a distance of 0.71, and its class is red. So our prediction for point C is that it should be red. But we know, because it's our validation data set for which we know the labels, we know it's supposed to be blue. So we will say no, it's not correct. And now we just calculate how many did we get correct and divide by the total number of classifications. And this is our correct classification rate. So we have 2 correct out of 3 classifications. So it's 2 out of 3. Now we move on to k equal 2. So for k equal 2, we will worry about the 2 closest points. So for A, we will worry about 0.1 and 0.2 this time. For B, we will worry about 0.7 and 0.5. And for C, we will worry about 0.7 and 0.5. Again, we will perform the prediction. This time we will try to find which class is represented more. So for point A, the 2 of them are green, so our prediction is green and it is correct. For B, the 2 points, the 2 closest neighbors are red, so our prediction is that it's red and it's correct. For C, again, we are making a mistake in the prediction and it's a wrong prediction because it's predicting red. So again, our correct classification rate for k equal 2 is 2 out of 3. We will do the same for k equal 3 without going through the detailed steps. So basically, we will be predicting A is green because 2 of the closest neighbors, 2 of the 3 closest neighbors are green, while the last one is blue. For B, 2 of the closest neighbors are red, while 0.6 is blue, so it's red. And for C, 2 of them are red, while 1 is blue, so we'll still predict red. So we're getting a correct classification rate of 2 over 3. So it seems that we got the same classification rate for k equal 1, k equal 2, k equal 3. And if you try out, I suggest you try out k equal 4 and k equal 5. You have the values over here. You will see that we will start deteriorating in our classification correctness. And you will start getting ties. So when we get ties, our algorithm will just randomly choose. So sometimes it could choose the correct value, but sometimes it could choose the wrong value. So what we will do is, as statisticians, we always prefer this, let's say the simplest model. So we will use k equal 1. So it's the smallest k that was giving us the correct classification rate desired. So from applying k and n on the validation set, we choose k equal 1. Basically, we're going with the smallest k for the highest classification rate. So if k equal 1 gave us 1 over 3, but k equal 2 gave us 2 over 3 as a correct classification, we will be going with k equal 2. So the most important thing is what correct classification rate we are getting. But since we got the same values, we're going with the lowest k because it will reduce the computational expense or complexity. Now we go to the fourth step. We will predict the classes for the test data. So now we agreed that we will use k equal 1. We might as well just start predicting for the test data. So these are our test points. We label them with, we index them with n and m. So we will find what is the closest neighbor to n and what is the closest neighbor to m. And as you can see graphically, it's easy. We know it's 5, and for m we know it's 6. But for a machine, this graph doesn't mean anything. So it will need to calculate the actual distance between every point and every other point. Like what we did in the first step for the validation set, we will calculate the distances to n and m from every point. And then we will sort the distances to find what are the closest points. And as we expect from the graph, the closest point to n is 5, while the closest point to m is 6. And then we will start predicting the classes based on the color of these k equal 1 closest points. So using k equal 1, we know that the closest point to n is 5, and 5 is red. So we will predict n is red. And for m, we know that the closest point is 6, so we will predict m as blue. Now, I advise you to try out what if we were using k equal 2 or k equal 3. Try to find what is the classification that will take place. So basically, finally, we classify the new observations. So we know that m is blue and n is red. In real life problem, the test data will also have labels. So you can check the correct classification rate on your labeled test class, test data, and report an error rate for your method. And you can only do this once because you already used your test data. So if you use it again, it will be violating the, let's say, the assumptions of data splitting. So don't use your test data until you are sure that this is the k value you want to use for your classification. And you can use your validation data as many times as you want. And you can use cross-validation if you want to go through more checks to find the best k. And hooray, congratulations! You just done k and n classification. And if you understood what happened exactly, you basically understand what's going on with the most complex software that is doing k and n classification. It's basically calculating the distances, finding the k nearest neighbors, checking these classes of the k nearest neighbors, and predicting the class of the new observation based on the majority of the k nearest neighbors. But you can imagine that it's a lot of calculation for a computer, especially if we're talking about millions of data points, which is very common in big data problems. And if we're talking about different number of dimensions. So in our problem, we used 2 dimensions, so it was easy to do the calculations. So you're talking about 10,000 dimensions of covariates, the calculation will be really expensive. And this takes us to the last part of this video, which is the strengths and limitations of k and n. So because we like k and n, we will start by the strengths. So as you have seen, we didn't do any parameter setting. So we did not assume any parameters in our data. We just went ahead and started calculating the distance. So it's an unparametric model that is very easy to implement on any data that can be distributed in any form of distribution. And it's easy to explain the decision rule. It's really easy, even for a 5-year-old kid, to explain that we are looking for the closest points and we are assigning the label based on those. So it's very useful for problems where you have to explain how the decision come about. While, for example, if you're using neural networks or if you're using random forests or bagging, it's going to be difficult to explain why this point is being classified as such. So if you're doing this problem for your stakeholders and you need to explain how the classification is done, it's also useful to think about methods that are easy to explain the decision rule. It supports nonlinear solutions. So really, the solution is not a linear decision boundary that's separating the data, like for example, LDA or SVM. It's basically, if you draw a decision boundary, it could be as wiggly as it can be, because it's just looking at the closest points to that new observation. So the solution is nonlinear. And it does not require covariates to be continuous. As we talked about in the distance metrics part, even if it's a binary covariate, we can measure the distance by different similarity indices. So we don't require it to be continuous, whereas some other methods, your covariate data, basically your x1 and x2, your explanatory variables, need to be continuous. With KNN, this is not a requirement. So these strengths are what makes you think about using KNN when you have an actual problem at hand. If it fits these, or if you need to overcome these things, you can use KNN. And it does not require a training phase. We really didn't fit a model. We just started calculating the distance directly and then assigning the observations based on these distances, or based on the k-nearest neighbors. Whereas some other methods, you will actually have to train a model. For example, if you're using a logistic classifier, you will have to fit a logistic regression model and then apply the prediction. But with KNN, you apply the predictions directly. It's just like, oh, what's the closest points to you? I have 3 closest neighbors, 2 of them are blue, 1 of them is red. Okay, you're blue. Next, without fitting any model. And it performs very well when your number of observations is larger than the number of covariates. So in our example here, for example, we have 5 red, 5 green, and 5 blue, so that's 15. 15 is much higher than 2. So our dimensions here are 2 dimensions, which is the number of covariates or explanatory variables, and it's the number of observations is much higher. But if we had 15 observations and our dimensions were 30, for example, KNN will start to deteriorate. The performance will start to deteriorate, and you need to start thinking about other methods, such as, for example, neural networks would perform well in such a situation. Now to the limitations that you need to worry about. The first limitation is the high computational cost. Even though you've seen a problem that was really easy to do by hand, but we needed to calculate the distance for every single point. So imagine if you have millions of points and your test or validation set has also millions of points, then you have to check the distance between every single one of these points with every number of training data that you have. So it doesn't work well with large data sets. And the computational complexity grows exponentially with the amount of data that we have. And it arrives at irregular decision boundaries. So some of the methods eventually arrive at a line, for example, and it's just an equation. Once you apply it to the new observation, if the result is positive, it will be this class. If it's negative, it will be this class, for example. But with KNN, you will still have to calculate the distance between every new observation and the millions of points that you already have, and then find the nearest neighbors and then aggregate their colors or classes. So it arrives at irregular decision boundaries. In some problems, we want a regular decision boundary that says, for example, if your blood pressure is over this limit and your sugar in the blood is above this limit, then the probability is that you have this disease or you don't have this disease. But with KNN, we cannot do this. And it requires scaling of the covariates data. So many times we don't want to change the scales of our data, so we need to think about other methods to use, such as, for example, classification trees. And with this, you learned KNN. Wait for the next video where we'll actually implement it in R using interesting data sets and trying to solve actual problems with KNN. Thank you very much for watching. If you like the video, please like it and subscribe, and wait for the next videos from our channel. Good luck with your data analysis.